Thank you for the invitation. So today I will talk about artificial intelligence-based tools for digital pathology and computational pathology. So artificial intelligence, AI, is a branch of computer science focused on development hardware and software that are the system for systems with like human capabilities. Machine learning is a subset of AI uses algorithm to analyze data, learn from it, and then make decisions. Deep learning is a more specialized branch of machine learning that utilizes neural networks to identify patterns and correlation that traditional computers cannot detect. Deep learning now is revolutionizing healthcare by enabling the development of predictive models that can tailor treatment to the individual, moving away and generalize one-size-fits-all approaches. In these slides, I report some highlights of the principal clinical application of deep learning in healthcare, specifically its role in personalized medicine. In recent years, significant advances have been made in the field of image analysis for melanoma diagnosis. Modern algorithms now can classify melanocytic lesions, detect key histological features such as tumor-infiltrating lymphocytes, TILs, and even predict mutational status of the tumor directly from the histopathological slides. These slides showcase various scientific studies that I found in the literature in which we can appreciate the accuracy of these deep learning approaches that go from 82% to 99%, reflecting so a growing precision of these AI-driven tools. Despite all these promising results, deep learning in healthcare still faces several critical challenges. The first one, of course, is the large VSI size, the large data set that we have to use to training the deep learning models, that we can be difficult to gather in rare pathology, and also the time-consuming manual annotation that is a significant bottleneck in which the expert pathologists that remain the gold standard for the annotation spent very time. There is some now annotation system, automatic annotation system, but the gold standards remain the annotation by pathologists. And finally, other limitations are due to the staining artifacts or color variation or artifacts due to the scanning process that can reduce the accuracy of these approaches. To date, deep learning is a relatively new research field. Here I report some papers that are divided into categories: based image analysis and advanced image analysis, and since from 2018. As I said before, the image analysis is divided in basic image analysis and advanced image analysis. The principal differences are that basic image analysis are divided in more simple tasks, so tumor detection, tumor subtyping. On the other hand, advanced image analysis is linked to survival prediction, mutation prediction, and response prediction to several different therapies. Here I report the principal kind of algorithms that are used in the melanoma studies, that are 4 different kind of algorithms that are divided in classification algorithm, regression algorithm, detection algorithm, and segmentation algorithm. The first one is the classification one. Classification algorithm that I have a categorical output. So here I report an example of a study that we published in 2020, in which we developed in collaboration with engineer Marco Laurino an algorithm that is able to distinguish healthy tissue from melanoma tissue. The second kind of algorithm that we use is the regression one, in which the output is a continuous variable. So in this case, this author develop an algorithm that was able to count directly from the H&E staining section the tumor infiltrating lymphocytes. The third category of algorithm that we can use in pathology is the detection. Also in this case we have a category output, but in this case the algorithm is able to recognize elements inside the histopathology tissue. For example, here it's able to discriminate, to distinguish from cancer cells, stromal cells, immune cells, and epidermal cells. And finally, the segmentation one that has an output, spatial localization, and target shape. Here I report a schematic overview of the pipeline of the VSI segmentation that is able to segment the whole slide image in superpixels and then capture the morphological attributes of the tumor. Now I will present you some results about two papers that we recently published. The first one that I said before, we published in 2020 and was a paper about the recognition of melanoma tumor tissue versus healthy tissue. And the second one that we developed in 2023, in which we developed an algorithm to recognize directly from the H&E stained tissue tumor infiltrating lymphocytes. The study includes 307 invasive primary melanoma tissue that we collected from 5 different Italian centers, and we divide this cohort in 5 data sets. The first 4 data sets we use for the training and validation phase, and then with the disjoint data set, the fifth, we use it for the testing set. Here I show you the pipeline of the proposed method application. Here we combine two different kind of algorithm, one of classification that refers to the first paper and one of regression. And if you can see from the workflow, the VSI was divided in a lot of superpixels, then undergo the first algorithm to the binary classification to melanoma versus healthy tissue, and then to the secondary. And the output of this process was a TIL density score. Here I'm showing you the validation and testing confusion matrix, in which you can appreciate the level of accuracy of this algorithm, because in the first phase of training and validation, we achieve an accuracy of 99.5%, and then in the testing 100%, because the algorithm was able to correctly recognize more than 29,000 untills correctly, with only 4 errors. The next steps was to try to correlate this automatic TIL index with the outcome of the patient. So we did the survival analysis. In particular, we did disease-free survival analysis and overall survival analysis. Here I'm showing you the disease-free survival analysis, in which in both the analysis univariate and multivariate, we reach the significativity, in which this, as we expect from the literature also, a positive correlation between the automatic ITIL score that we generated and the patient outcome. Similarly, we found the same correlation also for the overall survival. So, what we have to do to arrive to a translation of this research study to the clinical practice is not simple. This is obvious because there is some limitation. The first one was the approval for the regulatory agencies, and then if we want to have algorithms that have high quality, high accuracy, we need to enormous data set of images to have an high quality data, and then also a limitation by the financial cost. So concluding, pathologists need to be equipped with new methodology and tools to deliver the needed diagnostic sensitivity and specificity, and it now seems certain that in AI, or artificial intelligence, is, I think, a new step towards for precision pathology and precision medicine more in general. So I want to special thanks Professor Daniela Massi and all my collaborators at EBIR laboratory at University of Florence, and special thanks also to Engineer Marco Laurino, that from the National Research Council at Pisa, and of course you for your kind attention.